And this question says, what is the crystal field splitting energy? Very good. And how does the magnitude of delta O decide the actual configuration of d orbitals in a coordination entity? So there are two parts to the question. In the very first part, we're talking about the crystal field splitting energy. For that matter, you should be aware of what exactly is crystal field splitting. All the 5 d orbitals on any metal atom or ion are degenerate. What is the meaning of degenerate? That means all of them have same energy. So before any bonding happens, if you have any isolated metal atom or ion, then all 5 d orbitals degenerate. Has nothing to do with generators or electricity generators. All it means they have same energy. D orbitals. Which ones? All 5. All the 5 d orbitals are by default degenerate, but when they form complexes, when ligands come and combine, suddenly there is a division. Now you find that there is a groupism and these energies are no longer degenerate. That means you find that depending upon the geometry of molecule, they are affected in different ways. For example, in the case of octahedral field, there is energy gap, yes, and they split like this. In case of tetrahedral, the splitting may be different, but again, there is an energy gap. So what is essential is that an energy gap appears between different d orbitals which initially were degenerate. And this destruction of degeneracy is something which is called as crystal field splitting. After the degeneration, now this is now the written answer now which I am talking about, the previous was the explanation. The energy gap between the d orbitals after crystal field splitting has happened is called crystal field splitting energy. This is called crystal field splitting energy. For octahedral, it is denoted by delta O. For tetrahedral, you can use delta T, etc., etc. But delta is the symbol, capital delta is the symbol which is used to denote the energy gap between d orbitals after splitting, and that is measured in terms of crystal field splitting energy, that this is the energy gap between these d orbitals. That's the first part of the question. The next part says, how does magnitude of delta O decide the actual configuration of d orbitals in a coordination entity? Yes, very much it does. How? Watch this. There are 2 terms actually. Which are the 2 terms? Let me tell you. See, first of all, as you could see, delta O may be small or it may be large. Yes. Let me just draw 2 cases. One case in which delta O is small, and another case in which delta O is large. Okay. And large delta O happens usually with strong field ligands, and less delta O happens usually with weak field ligands. Okay. And now, say for example, you have a complex. I'm just giving an example just to explain that. A written part, I'll just put it ahead, no doubt. Now, say you have a D6 configuration. Yeah, let us start with D4. It will be much simpler. You have a D4 configuration. That means 1, 2, 3, 4. You had 4 electrons initially, and after splitting also, you should have 4. Now, what happens is 1, 2, 3. Till 3 it is fine. But the moment you want to put 4th electron, there is a problem. Why? If the gap is small, you find the electron jumps. It goes up. Okay. But if the gap is too large, then you find if it jumps up, it can't really go up, and it falls down and it pairs up like this. Oh wow, why does it not always pair up? See, pairing is costly. Why? For the very simple reason, if the same electron has to enter in any orbital which already contains one more electron, so there is bound to be electrostatic repulsion. And against this repulsion, I have to thrust this electron. That means that I have to spend some extra energy in that. And that, my dears, is called the pairing energy. So what is pairing energy? Pairing energy, P, represents the amount of extra energy I have to spend in pushing an additional electron in an orbital which already contains one more electron. So we are pairing that electron, so extra energy is required. That is called pairing energy. In this case, no pairing is needed, but I have to put electron up. In this case, pairing happens, and I cannot, push the electron up. Rather, it comes and pairs here. By common sense, can you not judge or can you not compare which is going to be large? Means, see, this is a case of the so-called high spin complex, and this is a classic case of a low spin complex. Can I compare delta O and P? Well, I might. In fact, I would be able to. How exactly? See, nature is very clever in calculations. If jumping up, please note, jumping up requires energy, extra energy. If jumping up is not costly and pairing is difficult, that means if jumping up is less, it costs you less. If crystal field splitting is small and pairing energy is higher, electrons don't want to pair, they just jump up and it becomes high spin. And if jumping up is costly and pairing is cheaper, if delta is very large as compared to P, you find they pair up and there is a low spin complex. So it's as simple as that. If delta O is less than pairing energy, you get a high spin complex. If delta O is more than pairing energy, you get a low spin complex. And this is the meaning of exactly how does delta O decide the actual configuration of d orbitals in a coordination entity. I hope you've understood this. I'll just show you some write-up also on that in case you are interested in seeing how to write down the theory. This is a standard theory response to this. You can take a screenshot, write it down, but then students often complain that they don't understand what is written here. I have given you a very good example of the same thing by writing it down there.